Hi class, welcome to Unit 10, Redox in Electrochemistry. We're going to begin this unit with a review on how to assign oxidation numbers. By the end of this video, you should be able to assign oxidation numbers to elements, ions, and compounds. I know this is review, but make sure you take notes. Use the guided notes provided or take your own. Let's get started. In all electrochemical reactions, electrons are transferred from one species to another. The gain and loss of electrons can be tracked using oxidation numbers. So let's talk a little bit of terminology here. Oxidation is a process where we lose electrons. This causes an increase in the oxidation number because electrons are negative. Metals very commonly react with oxygen and are oxidized, forming positive cations. And when we write electrochemical equations that represent oxidation, the electrons are on the product side as they are lost. Reduction is the reverse. During reduction, we gain electrons. Gaining electrons, which are negative, cause a decrease in the oxidation number. Nonmetals are commonly reduced, and electrons appear on the reactant side of the reaction for reduction because electrons are gained. Do you remember why electrons are transferred? Species tend to gain or lose electrons in a quest to obtain more stable, lower energy, noble gas valence electron configuration. Again, as a review, cations or positive ions are formed when electrons are lost. We can remember this using the mnemonic device, Leo the lion says grr. Leo, the loss of electrons is oxidation. When you lose electrons, the species will become smaller. So here you can see the magnesium atom whose electron configuration is 282. When magnesium loses 2 negative electrons, it obtains a positive 2 charge because it has 12 positive protons but only 10 negative electrons. When magnesium has the electron configuration 2,8, it has an electron configuration like the noble gas neon. The opposite is true for the formation of anions. Anions are a negative ion. Anions are formed by the gain of electrons, thus reducing the oxidation number or charge. Gaining electrons causes species to grow in size. Nonmetals, like chlorine, commonly form anions. Here you can see when a chlorine atom with no charge gains 1 valence electron, it obtains a negative 1 charge. It has 17 positive protons, but 18 negative electrons. When the chlorine ion has the electron configuration of 288, it has an electron configuration just like the noble gas argon. Recall that the oxidation numbers found on the reference table are the possible charges other than 0 that an element can have. Recall from earlier in the year that this is the periodic table of neutral elements. So when we have lone atoms, their oxidation numbers are always 0. The oxidation numbers shown on the periodic table are only the oxidation numbers of the species when bonded. Again, the reason why atoms form bonds and thus gain or lose electrons is to obtain stable, low energy, noble gas valence electron configuration. Whether alone or in a bond, these species will always have a total neutral charge. Again, in Lesson 30, we learned these 4 rules for assigning oxidation number. If you are not maintaining a neat and organized notebook, please pause the video and copy down these 4 rules. If you are maintaining a notebook, just refer to your notes for Lesson 30. Let's see if we can use our periodic table to help us find the oxidation number of various species. Beginning with this example, tin, this is a lone element, has no charge and no partner, so its oxidation number is 0. Now here we have element number 7, nitrogen. Now this nitrogen, again, it has no charge and has no partner. Nitrogen is one of the 7 diatomic elements. So here it is a free element, so its oxidation state is also 0. In this example, we have chlorine, which is element number 17. This chlorine has a -1 charge, indicating that it has gained an electron. Here, they gave us the charge, so we know the charge is given. Remember, a 1 is understood. That rule applies here to calcium. They give us the charge. If you're given the charge, that is the oxidation number. Let's look at chromium oxide. Chromium, element number 24, has 3 oxidation states, +2, +3, and +6. So we don't know which oxidation state chromium has here, but when we look at its partner oxygen, in a bond, oxygen only has the oxidation state of -2. Now chromium oxide is 1 chromium and 3 oxygen atoms. Each oxygen has a -2 charge. So that means that this total charge is -6. So the chromium must have a charge of +6. This species is called chromium 6 oxide. Let's look at this species. So here we have 3 different elements. We have a sodium, a bromine, and 3 oxygens. Now, when we look at sodium, element number 11 on our reference table, the charge it always has in a bond is +1. And again, oxygen, element number 8, only ever has the charge of -2. Now, when we look at bromine here, element number 35, it has many oxidation states, but we can use the oxidation states of its partners and the knowledge that this entire system has 0 charge, like those stable noble gases, to figure out the charge of the bromine. So if this here is a total charge of -6, and this is a +1, then the bromine must have a charge of +5. Let's look at magnesium sulfate. Here, magnesium is with the polyatomic ion sulfate. We could do something similar to here because we know that the total charge of this here is 0. But on reference table E, they also tell me that the total charge of sulfate is -2. So I can use this as a shortcut. I know each oxygen carries a charge of -2. So I have to ask myself, what is the single charge that the sulfur must have to counter out the -8 from the 4 oxygens to equal -2? In this case, sulfur has to be +6. Now, if I want to check my work, recall that the total species should have a charge of 0. And magnesium, element number 12, has a charge of +2. So when I add up all of the charges, this is a +8, this is a -8, so the total system equals 0. We can find our answer with or without the shortcut. Let's do one more example together. Here we have 1 single calcium, 1 single chlorine, and 3 oxygen atoms. Oxygen in a bond always has a charge of -2. And chlorine could have many charges, but when we look at calcium, it can only have a charge of +2. Here, algebra tells me that chlorine here has a charge of +4. So we can remember the difference between oxidation and reduction using one of 2 mnemonic devices. The first mnemonic device is Leo the lion says grrr. Leo, the loss of electrons is oxidation. Grrr, the gain of electrons is reduction. This can also be remembered using oil rig, as oxidation is loss of electrons and reduction is gain. Let's look at a single replacement reaction where we can identify how oxidation numbers are changing in the reaction so that we can determine which species is gaining electrons or undergoing a charge reduction and which species is losing electrons and undergoing a loss of electrons. So here in this single replacement reaction, we know that this is a spontaneous reaction.
So we use reference table J to determine that this reaction will be spontaneous. That is because the metal potassium that is alone, found here, is more active than the metal iron, found here. Since the lone element is more active, it is better at bonding to obtain stable noble gas valence electron configuration, thus making this reaction spontaneous or exothermic.
Because systems in nature are spontaneous when they have higher entropy or disorder and lower energy. So when we look for the disorder is staying the same because we have one solid and one aqueous species on each side. So it must be spontaneous because it has lower energy, meaning it's exothermic. Recall that exothermic reactions release energy because their heat of reaction is negative. That means if I had to write the energy into this reaction, it would be a product. It would be after the arrow. Now let's see how we can find oxidation numbers. We begin here with potassium, but this potassium is all by itself. It is a lone element, so its oxidation state is 0. And here we have iron and chlorine in a compound. We know that the total charge of this entire compound is 0, but we have 1 iron and 2 chlorine ions. Now, iron can have a +2 or a +3 charge. So when iron bonds with chlorine, chlorine must be negative. So the charge of the chlorine has to be -1. Since each chlorine is -1, that gives me a total charge of -2, meaning that this iron has a +2 charge. It could be helpful to write the oxidation number of each species in the upper right-hand corner, just like it is on the periodic table. Here, again, we have iron. Iron is by itself, though, so that means it's an atom of iron. It has the same number of protons, 26, as it does electrons, so its charge is 0. And one more time, we have potassium chloride. Now, we can ignore the coefficient when trying to determine the oxidation numbers, but we can see that in a bond, potassium always has a charge of +1. If there's a potassium with a +1, then chlorine must be -1. So let's see what this means for the total reaction. Since this is an exothermic reaction, can you predict what the potential energy diagram will look like? This is review from our last unit, kinetics and equilibrium. So when we look at the potassium, you can see that the potassium's charge has changed from 0 to +1. So its charge has moved from here and gone this direction. So its charge is increased. When you increase a charge, it's not reduction, but instead it's called oxidation. Now, in oxidation, we are losing electrons, so they're here on the product side. Because when we write a balanced chemical reaction, not only must the atoms be conserved, but so must the charge. So when we look at the charges here, we have 2 times 0, or 0, equals +2 plus -2. So that balances this reaction. And when we look at the iron, we can see that the iron has changed charge from +2 to 0. So that means that the iron's charge has moved from +2 to 0. It has gone down, thus meaning it has undergone a reduction in charge. So here we can see that the +2 ion plus 2 negative electrons equals 0. So charge is conserved. So the word reduction refers to how the charge changes. Since matter cannot be created or destroyed, the loss of electrons must always be accompanied by the gain of electrons, meaning an oxidation always happens at the same time as a reduction. This concludes lesson number 56, assigning oxidation numbers. Make sure you've written down any questions you have and completed your homework. I'll see you in class.